Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, we are going to learn about polyaromatic hydrocarbons. So what is polynuclear hydrocarbons and what is its properties we will discuss. So polynuclear hydrocarbons, a polynuclear aromatic hydrocarbon is a hydrocarbon made up of fused aromatic ring molecules. These rings share one or more sides and contains delocalized electrons. Another way to consider polynuclear hydrocarbons, in short FAS, is molecules made by fusing two or more benzene rings. Polynuclear aromatic hydrocarbon molecules contains only carbon and hydrogen atom. What is the properties of this class of organic compound? Polynuclear aromatic hydrocarbons are lipophilic, non-polar molecules, and they tend to persist in the environment because polyaromatic hydrocarbons are not very soluble in water, while 2 and 3 ring FAS are somewhat soluble in aqueous solution. The solubility decreases nearly logarithmically as molecular mass increases. 2, 3, and 4 ring polyaromatic hydrocarbons are sufficiently volatile to exist in the gas phase. You also know while larger molecules exist as solid, pure solid, FAS may be colorless white, pale yellow, and pale green. My friend, what is the sources of FAS? FAS are organic molecules that form from a variety of natural and environmental pollutant reactions. Natural FAS form from forest fires and volcanic eruptions. The compounds are numerous in fossil fuels such as coal and petroleum. Main contribution polyaromatic hydrocarbons by burning wood and by the incomplete combustion of fossil fuel. The compound occurs as natural consequence of cooking food, particularly when food is cooked at a high temperature, grilled or smoked. The chemicals are released in cigarette smoke and form from burning waste. Now, what is the health effect of FAS? Polynuclear aromatic hydrocarbons are extremely important because they are associated with the genetic damage and disease. Also, the compound persists in the environment, leading to increased problem over time. FAS are toxic to aquatic life. In addition to toxicity, these compounds are often mutagenic, carcinogenic, and teratogenic. Parental exposure to this chemical is associated with the lowered IQ and childhood asthma. My friend, people get exposed to FAS from breathing contaminated air, eating food that contains the compounds, and from skin contact. Unless a person works in an industrial setting with these chemical exposure tend to be long term and low level. So there are not medical treatment to address the effect. The best defense against health effect from polyaromatic hydrocarbon exposure is to become very aware of situation that elevate risk, breathing smoke, eating charred meals, and touching petroleum products. Now, friend, from here you can learn your BSC syllabus like classification polynuclear hydrocarbon. There are two classification, benzenoid and non-benzenoid. This is the example of non-benzenoid, which is azulene, and this is the examples of benzenoid. There are two types of benzenoid. One is the refused ring, another is isolated. This is biphenyl, and this is the linear, and this is the angular combination. Examples of angular combination is phenanthrene, and examples of linear combination of naphthalene and anthracene. Now, friend, naphthalene. Now, my friends, start with the naphthalene. Naphthalene, carbon 10 and hydrogen 8, 2 carbon less than carbon, is an aromatic hydrocarbon in which two benzene rings are fused into ortho position. For the purpose of naming its derivatives, the positions are independently incredibly indicated figures. You can see the numbering start from this carbon, either this carbon or this carbon. So total you have to give the 8 carbon numbering, and there are 2 carbon here which is fused position. Now isolation from coal tar. Naphthalene is the largest single component of a coal tar, about 6 to 10%. The hydrocarbon was first noticed as deposit in the condense during the distillation of naphtha fraction, and hence its name naphthalene. It is obtained chiefly by cooling the middle aisle fractions at 60 to 230 degrees Celsius, whereupon the naphthalene crystallizes out. The crude crystals are removed by centrifuging. These are melted and then treated successively with concentrated sulfuric acid to remove phenols. And finally, naphthalene is sublimed to give the pure product. Now, my friend, properties. Physical properties of naphthalene. Naphthalene is a white solid which crystallizes in shining plate, melting point minus 80 degrees Celsius, boiling point 218 degrees Celsius, having a strong odor. It is very volatile and sublimes readily on warming. Naphthalene is insoluble in water but dissolve easily in organic solvent, particularly in ether and benzene. Now, chemical properties. The reactions of naphthalene are essentially the same as those of benzene. It undergoes substitution readily and form addition product. However, it is somewhat less aromatic than benzene. Thus, the double bonds in naphthalene exhibit in part the reactivity of the alkenes, and it forms addition compounds some readily than does benzene. As soon as one of the ring is fully saturated by addition of hydrogen or halogens. Now, my friend, resonance structure of naphthalene. X-ray diffraction study shows that unlike benzene, all carbon-carbon bond in naphthalene are not of the same length. In particular, the carbon 1 and carbon 2 bond is considerably shorter, 1.36 angstrom, than the carbon 2 and carbon 3 bond, 1.04. This difference can be understood if we examine this resonance form given below. Notice that the carbon 1 and carbon 2 bond is double in two structure, 1 and B, and single in only one, C, whereas the carbon 2 and carbon 3 bond is single in two structure, A and B, and double in only one. So, we would therefore expect the carbon 1 and carbon 2 bond to have the more double bond character, shorter bond length, and the carbon 2 and carbon 3 bond to have more single bond character, longer bond length. So, the resonance structure of naphthalene is about 60 kilocalorie per mole, and this value is less than twice the amount of single benzene ring. As a result, naphthalene is somewhat less aromatic, more reactive than benzene. So you can see here 1 2, 1 2, and 1 2. So one structure have the single bond and two structure have double bond in between one. So this is more double bond character. Now 2 3, 2 3, and 2 3. Only one double bonds, two single bond. So this is the single bond character. 2 3 4, 3 4, 3 4, 3 4. This a bond is double bond character more than single bond character. Now, my friend, preparation of naphthalene from 3-benzoyl propanic acid. When 3-benzoyl propanic acid is heated with sulfuric acid, alpha naphthol is formed, which on distillation with zinc dust forms naphthalene. So this is the your 3-benzoyl propanic acid. This is zinc amalgam here and forming 4-phenyl butanoic acid. 4-phenyl butene undergo reaction with calcium and heat. Naphthalene will form. Now, Howard's synthesis. If you have benzene, it involves in 5 steps. Benzene and succinic acid, it gives 3-benzoyl propanic acid. And then 3-benzoyl propanic acid undergo reduction, you will get 4-phenyl butanoic acid. And then this will converted into tetralone from 4-phenyl butanoic acid. Now tetralone, this compound is tetralone, undergo zinc amalgam, you will get the 1, 2, 3, 4 tetrahydronaphthalene tetraline. This is tetralone. And now this tetraline undergo palladium and heating, you will get the naphthalene. Now reaction of naphthalene. Naphthalene is more reactive than benzene. It undergoes several reactions like oxidation, reduction, addition, nitration, halogenation, acylation. So oxidation of naphthalene. You can see oxidize it give phthalic acid. In case of KMNO4 it give thalonic acid. In chromic acid it will give 1,4-naphthaquinone. And then in the presence of zinc and ozone, thialdehyde, in presence of mercuric sulfate and sulfuric acid, phthalic anhydride. So now reduction of naphthalene. You can see the reductions. Naphthalene undergo reduction, it gives tetraline. In presence of nickel, decaline. It undergo reduction in the presence of ethanol, sodium. It gives 1,4-dihydrodecaline. They undergo H2 nickel, decaline. In presence of sodium, alcohol, form tetraline. Now addition reaction. The addition of bromine or chlorine to naphthalene give naphthalene dibromide or naphthalene dichloride. Further addition of bromine or chlorine result in the formation of phthalene tetrabromide, naphthalene tetrachloride. Look at here, naphthalene, 1,4-dibromonaphthalene, 1, 2, 3, 4 tetrabromonaphthalene. And again, chlorination, naphthalene undergo chlorination, it gives alpha chloronaphthalene. So that is very important. Here is some symbolic mistake, so you can care about this. Now electrophilic substitution reaction. Naphthalene like benzene undergo electrophilic substitution reaction. Substitution occurs primarily at carbon 1 alpha position, and this can be understood if we examine the intermediate carbonium ion. Two resonance form can be written for the intermediate carbonium ion obtained from the attack at carbon 1 without involving the other ring, whereas only such form is possible for substitution at carbon 2. E plus is the following equation represent an electrophile. So naphthalene, you can see E plus attack this carbon. So there is a bond formation between carbon and E. Automatically this charge transferred to the neighbors here, and then it is resonance stabilized and forming one substituted product. If attack at carbon 2, then positive charge he is here less stable and forming two substitution product. So consequently the former intermediate is more stable and product with a substituents at carbon 1 predominates. Substitution at carbon 2 beta position occurs only when the reactions are carried at higher temperature or when bulkier solvent are used. Now nitration of naphthalene, you can see, give the alpha nitronaphthalene. Now halogenation reaction, naphthalene in presence of iron catalyst react with the halogen to form alpha substituted naphthalene. You see the alpha chloronaphthalene. Sulfonations, naphthalene, low temperature it gave for one products means alpha positions, one sulfonic acid, and at high temperature naphthalene to sulfonic acid. Friedel-Crafts alkylation. Friedel-Crafts alkylation at low temperature is carried out for naphthalene, which reaction with the hydromethane to produce 1-methyl naphthalene as a major product and 2-methyl-naphthalene as a minor product. Look at here, naphthalene react with methyl iodide, it gives 1-methyl-naphthalene major product and 2-methyl-naphthalene minor product. Now, Fettel-Crafts acylation. Naphthalene undergo Fettel-Crafts reaction with acetyl chloride to form alpha or beta product depending on the reaction condition. You can see the naphthalene at presence of nitrobenzene polar solvent, it gives methyl 2-naphthyl ketone, and in non-polar solvent, it gives methyl 1-naphthyl ketone. Now you can see derivative of naphthalene, naphthalene 1-ol, naphthalene 1,5-diol, naphthalene, you can see 4-amino, 3-hydroxynaphthalene, 1-sulfonic acid. Now medicinal uses of naphthalene. Production of naphthols, alpha-naphthol, production of dyes, phenyl azo beta naphthol dyes, preparation of beta blocker drugs, propranolol, and to synthesize synthetic dyes, and useful in insecticide. Veterinary medicine, dusting powder, polyethylene naphthalene to prepare plastic bottles, naphthalene sulfonic acid are used to prepare plasticizer, natural rubber, and naphthalene drug to cure cough, urine infection, eye trouble. Now, my friend, phenanthrene. You know, phenanthrene is a cyclic aromatic hydro compound composed of three fused benzene rings. In its pure form, it is found in cigarette, smoked, and is irritating photosensitizing skin to light. You know, phenanthrene appears as a white powder having blue fluorescence. Phenanthrene is the backbone of morphine. You can see the structure of phenanthrene, angular arrangement of three fused benzene ring. Now, resonance structure of phenanthrene. Like anthracene, phenanthrene is a planar molecules. All 14 carbon atoms are sp2 half-die. The sp2 orbitals overlap with each other and with the orbitals of 10 hydrogen atom to carbon-carbon and carbon-hydrogen sigma bond. Each carbon atom also possesses a p orbital, and these are perpendicular to the plane containing the bond. The lateral overlap of this p orbital produces a pi molecular orbital containing 10 electrons. Phenanthrenes show aromatic properties because the resulting pi molecular orbital satisfied the Haeckel's rule n is equal to 3 in 4n plus 2. Look at here this 5 structure and resonance energy 91 kilocalorie per mole. Now preparation of phenanthrene. Harvard phenanthrene synthesis. Starting from naphthalene, succinic anhydride, it gives 4 naphthalene, 1 aryl, 4 oxobutonic acid, then undergo zinc amalgam reductions. In presence of acid, it gives 4 naphthalene, 1 butonic acid, and in presence of sulfuric acid, cyclization occurs, it gives 3,4 dihydronaphthalene, 1 2H on, and again zinc amalgam reduces this CO bond to CH2 1 2 3 4 tetrahydrophenanthrene form, and it undergo reduction in presence of selenium palladium, you will get the phenanthrene. Reaction of phenanthrene, reduction, phenanthrene undergo reduction in presence of alcohol and sodium, you will get the 9,10 dihydrophenanthrene. In case of in chromic acid, you will get 9,10 phenanthrone, and oxidations in you will get the 9,10 phenanthroquinone, and after that further oxidation will break the carbon-carbon bond and diphenic acid will form. Bromination, phenanthrene, it undergo bromination, you will get the 19 dibromide, and further in heating you will get the single bromine 9-bromophenanthrene. Now electrophilic addition versus electrophilic substitution. So phenanthrene have the two products, one addition product, one substitution product. So you can see if electrophile is approaching positive charge is here, there is substitution product and another is addition product. In case of anthracene, you have the substitution product, you have the addition product. Now reactivity of 9 and 10 position toward electrophilic attack, where whether reaction lead to substitution or addition is understandable since the initially formed carbocation is the most stable one. in which aromatic state are preserved in two of the three rings. You know, my friend, this carbocation can either give a proton to yield the substitution product or accept the nucleophile to yield the addition product. And that is very important, addition and substitution. The tendency of this compound to undergo addition is due to the comparatively small sacrifice in resonance energy. So, derivative of phenanthrene, you can see the papaverine, ribo, paraviforines, colonine contains and codeine contains this ring. Now, medicinal uses of phenanthrene. Anthraquinone is used in the manufacture of alizarin and several other dyes which contains phenanthrene and dethranol antifungals. You can see the structure, and steroidal moiety contains phenanthrene nucleus, and sex hormone and bile acid contains this ring. Steroid used as the oral contraceptive and anti-inflammatory agent, and cardiac glycosides, morphine, codeine. Now, anthracene. You know, friend, anthracene is present in coal tar to the extent of 0.3 to 3.5%, hence its name Greek anthracene meaning coal. On distillation of tar, it passes over in high boiling fraction anthracene oil. The molecules of anthracene is made up of three benzene nuclei fused in ortho position, and it is colorless solid polycyclic aromatic hydrocarbon. Look at the structure of anthracene. Now, this is the resonating structure. So, X-ray diffraction study shows that, like naphthalene, all carbon bonds in anthracene are not of the same length. In particularly, carbon 1 carbon 2 bond is considerably shorter, and carbon 2 and 3 bonds longer. And this difference in bond length can be understood if we examine the four resonating form given below. Notice that the carbon 1 and carbon 2 bond in double in 3 structure ABC, and the single in 1, whereas this carbon 2 and carbon 3 bond is single in 3 structure, the double in only 1. We would therefore expect the carbon 1 and carbon 2 bond to have the more double bond character, shorter bond length, and carbon 2 and carbon 3 bond to have the more single bond character, longer bond length. So, the resonance energy of anthracene is 84 kilocalorie per mole, and this average to 28 kilocalorie per mole per ring, which is subsequently lower than that of benzene, 36 kilocalorie per mole. As a resulting, anthracene is much less aromatic than benzene and behaves more like a saturated aliphatic hydrocarbon. So, you can see the structure A, B, C, and D. Now, preparation of anthracene by Friedel-Crafts reaction. Two molecules of benzyl chloride is condensed in presence of AlCl3 to produce anthracene. You can see by Haworth synthesis. Phthalic anhydride react with benzene, it gives orthobenzoyl benzoic acid. In step 2, you can see the orthobenzoyl benzoic acid undergo cyclization. It will give the 9,10 anthraquinone, and distillation of 9,10 anthraquinone with zinc dust will produce anthracene. You can see 9,10 anthraquinone undergoes zinc distillation, it gives anthracene. Now, Ellipse reactions. Ellipse reaction, pyrolysis of orthomethyl benzophenone at 450 degrees Celsius can produce anthracene. So, this is the now Diels-Elder reactions. You can see the reaction scheme. 1 for naphthaquinone undergo diene reactions in presence of tin tetrachloride. Diels-Elder product will form. It undergo reaction with the chromium oxide in acetic acid. You will get 9,10 anthraquinone. Undergo zinc distillation. It gave the anthracene. Now, properties of anthracene. Anthracene is colorless solid. It melts at 280 degrees Celsius and boils at 340 degrees Celsius. Anthracene is insoluble in water but dissolved in benzene. It shows a strong blue fluorescence when exposed to ultraviolet light, and this fluorescence property of anthracene is used criminal detections work, since a small amount of finely powdered anthracene on clothing, skin, money, etc. It is not detected under the ordinary light but easily detected and noticed when exposed to ultraviolet light. So, chemical Anthracene undergo addition and electrophilic substitution reaction, and this reaction preferentially occurs at carbon 1, 9 and 10 position. And this can be understood. We examine the intermediate carbonium ion obtained from attack at carbon 1 and carbon 2 and carbon 9. All other possible are equivalent to either 1 and 2 or 9 by symmetry. So E plus is the following equations represent the electrophile. You can see electrophile attack at one position, there is a 2, an attack at 2 position, there is a 1, an attack at 9 positions, so there is a 1. So attack at 9 yield a carbonium ion intermediate in which two benzene rings are retained, whereas the attack carbon 1 and carbon 2 yield an intermediate in which naphthalene system is retained. The former intermediate is more stable and its formation of favored because the resonance energy of two benzene ring exceed that of naphthalene. So now you understand why anthracene 9 in anthracene 9 position is important for electrophilic, because two benzene ring is uh, which is equal to 72 kilocalorie per mole. Now reaction of anthracene. Electrophilic substitution reaction. You can see the anthracene undergo halogenation. You will get the 9 haloanthracene and anthracene 1 sulfonic acid, anthracene 2 sulfonic acid undergo sulfonation and nitration and 9 nitroanthracene. Now, you can see the anthracene undergo acetylation in nonpolar solvent. You will get 9 acetylanthracene. Acetylation in polar solvent, you will get 1 acetylanthracene. And high temperature H2SO4, you will get the anthracene 2,7 disulfonic acid. Low temperature anthracene 1,8 disulfonic acid. Now, Diels-Alder reaction. Anthracene undergo Diels-Alder reaction at 19 position and form indo-anthracene malic anhydride. So this is the anthracene malic anhydride. You will get Diels-Alder. Now oxidation. Anthracene undergo oxidation. You will get the 19 anthraquinone. Now reduction. Anthracene undergo reduction. It gives nitrate dihydroanthracene. Now dimerization. Dimerization of anthracene and in UV light produces dianthracene. So derivative of anthracene, anthraquinone, anthrone, xanthone, and anthrol. Now, medicinal uses of anthracene. Anthracene glycosides are oxygenated derivative of pharmacological importance, and that we use as laxatives or catharetics, antineoplastic agents, polycystic kidney. You can see the structure of imodine. Anti-inflammatory, antibacterial, antifungal, anti-proliferative activity. You can see the cryosophenol and yellow imodine. As a natural dyes, hepatoprotective, nephroprotective antioxidants, this is rain. Now friend, diphenyl methane. This is the structure of dimethyl methane. Now preparation, you can see how you will get the benzene and benzyl chloride. You will get the diphenyl methane, and then this is the diphenyl methane. Derivative of diphenyl methane is like benzohydrol, and benzophenone is the derivative of diphenyl methane. Medicinal uses of diphenyl methane is widely used in the synthesis of luminogens for aggregations induced emissions. Diphenyl methane potassium used in the preparation of polymerizations. Now triphenyl methane. You can see the structure of triphenyl methane. Triphenyl methane is the chromogen of a large number of dyes. Diphenyl methane dyes are very brilliant intense color but fade quickly in light. Therefore, they are no longer much used on textile. However, they are used in large quantity for coloring paper and typewriter ribbons, where patience to light is not so important. So preparation of triphenyl methane, starting from chloroform and benzene, you will get the triphenyl methane. And derivative of triphenyl methane, you can see gentian violet and odine. These are the derivative. Now you can see the crystal violet, malachite green, all contain diphenyl triphenyl methane medicinal uses. Now you can see the crystal violets. Triphenyl methane is used in copying papers, in hectographs and paintings in triphenyl methane. So my friend, these are the references. So my friend, I hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching.